these labs where they're just, matching or pick one. I don't always do the best job of checking each one every year because you assume the computer saves the answers, and somehow one of the correct answers it went away. So you had two options that were incorrect. One of the right options we wanted, see, I gotta do the U first, is microfarad is what we wanted. So it would have been 0.5 microfarad. If you were to convert it, that's what I wanted to pick. Now Nick knows how to work computers better than me in Moodle. So I said to him, rats, I'll change it for next year, but I can't change it for this year because everybody that went into it, it gets funny, right? Because if I change it, and then you're like, you changed the answer on me, so then there's multiple. So I started to do that, and he's like, no, I can push the regrade button. And he was telling me something about regrade. To be honest with you, I do not understand what he's trying to tell me. So I went in there and manually graded that one. If when you have it open, microfarad, 0.5 microfarad is not one of the answers that you can pick for number 15. Just pick any one you want, and I've got a sticky note on my desk to a week or two from now, go back through and basically mark number 15 correct on everybody's lab. Just my fault. So that's what's up with 15. So quick review on those. It's really a review from Christina's class, but let's say we had that many. We'll say volts. And part of this class is weird, right? You're like, I don't know what a volt is. I'm like, yeah, it's because it's today. But I couldn't teach you volt. Anyway, so the point is that was a review one. You'll learn what volts and amps and farads and henries and all that stuff are later. But you could put anything you want here. You could put volts, you could put tikis, you could put geese. So, it's the idea. So we'll even do that just for the fun of it. We'll say you've got one of tiki's hairs, so we're checking how much mass of tiki you have. It's 0.0006. Tiki's, I want to know how many millitikis that you have, right? That's basically what the lab was. Is this just saying, hey, you just got to move decimals around. What was at the end was basically irrelevant. So to get from that to millitikis, we know if this doesn't have a suffix, milli is 10 to the -3, right? So I just got to move the decimal 3 places. 1, 2, 3. And that's how I do it on all those homeworks, which is why when I'm taking exams, I have a scratch piece of paper. I'll write the number out on the scratch piece of paper, move my decimal. So you would have 1, 2, 3, 4, 4 zeros. Millitikis. Well, I still don't like that number, so maybe I wanted micro tikis. If I wanted micro tikis, that's 10 to the -6 of the regular, right? But if I started at milli and I want to go to micro, the difference between 3 and 6 is just 3 more. So I can just go, let's go 3 more. 1, 2, 3. All right, so we would have had 0.06 micro tikis if we had one piece of her hair. If I wanted to go way the other way and say I have 0.06 micro tikis, how many kilotikis is that? I could take that 0.06, and if I gotta get to kilo, how many decimals do I gotta move? I gotta move 6 to get to my baseline, and then kilo is 3 more, so I gotta move 9 total. So what I do on here is I actually put a bunch of zeros all lined up. I should have wrote it on the left side of the board. And I say I gotta move 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, I've got that many kilotikis if I have one of her hairs. And I go back and count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros before my number. All right, so everybody clear on that for that lab? It's not really an electrical lab, it's actually a mathematics lab with Christina. That was review. But we'll use it all the time in electrical because our numbers might be all over the board. Okay. There's that review. Tomorrow we're going to get your volt meter. solder, I guess I'll put it that way. So that'll be coming up. Don't go take all that stuff I set out and run away with it yet. I'm just getting it set up so it's easy for us to demo tomorrow. Try not to move stuff around in the boxes, so I'll give you more instructions with that when we get there tomorrow. One thing is, I did get more 3/8 tubing in the mail from Amazon. It's the cheapest place, go figure, right? I didn't like how the tube showed up, and it reminded me that, I don't know if I ever showed you guys how to unroll a tube of this stuff. So let's say you got this and you need a 6-inch piece. You absolutely do not want to pull the middle 6 inches out. That would be the wrong way to do it. So I used to do this in refrigeration all the time, where they'd come in a 50-foot roll. Sometimes they were, 1 inch. So in refrigeration, we'd actually stand on it and unroll it. This stuff's smaller. Basically, you need to put it on a flat surface, and you just unroll it flat. And you'll end up with a nice straight. So I'll probably add that to my class next year, take a picture of this. Back to, we can't teach you everything. I don't want to teach you all Ryan's classes and Christina's work hardening. You wouldn't want to roll this back up, straighten it up, roll it back up, and straighten it out, because we're going to work harden it. That's one of the issues with being rolled this tight. You can kind of get away with it once when they manufactured it, and you can tell it rolls out pretty straight. It'll do that if I rolled the whole thing out, as long as you have it, especially on a hard, flat surface. And that's where in the refrigeration world, we do a lot of this. I don't know how many hundreds of times I did that. With copper pipe, it does the same thing, and you end up with a nice long straight piece. So I might roll this back up, but I don't really want to work harden it, so I haven't decided yet. I'm going to set it aside today. I'm more likely just going to cut this off and put it somewhere, because we don't want to go back and forth. But if you need to unroll your tubing, that's how you generally do it. Hard surface, roll it out. I'm going to add that to next year's lecture. That stuff's about $1 a foot, so if you want to practice 1 or 2 more, try to use scraps. But we do have more if it gets around to it. Okay. Okay. We are going to go over the hand rules all kinds of times throughout this class. Yesterday was kind of an intro to get you familiar with some of our terms and whatnot. Today is going to be a lot more math and terms like volts, amps, and the very basic math that goes with it. But without knowing that the hand rules exist, as we go through the rest of class, when I want to introduce a concept, it gets hard to introduce a concept without you knowing that there are hand rules. So, how many hand rules are there? 4 hand rules, very good. So 2 of them are curl hand rules, which I do everything in conventional. So they're going to be conventional, which means it's going to be right hand curl rules. So right, right, in our little dance, right? So those are both the curl rules. I added this little thing to the to-do list. I found some compasses and put them on a sheet of paper. Compasses generally point north, right? The blue line is, hard to see, and that's why I need to do it better. But the blue line is generally pointing north. If I pass electricity through a conductor, it's going to make those flux fields. And the fields are going to be circling that wire in a direction. It's our hand curl direction. And the flux lines go inside the magnets from south to north, outside the magnets, north to the next south. So, if I just hook this up to a battery, I have a light bulb so we don't blow it. Notice one blue is pointed one way and one blue is pointed the other way. I'm going to highly recommend you kind of do this on your own or come see me. What I'd love to have is a little 6-inch kind of table that these things are just glued to, that my wire can go through, and it'd make it easier instead of a flimsy piece of paper, right? So that might be a project somebody can do, is make me a little 4-inch table. I actually have more compasses coming. But, so, with that said, and it's always hard to do, my fingers are curled the wrong direction there, right? Because I want to go from the silver to the blue. So my fingers are curled the wrong direction. So I'd have to curl my fingers this way, which means my hand's upside down now. So that tells me that the current through my wire is going down through the wire. And that's conventional. So if I trace this backwards, I find that, oh yep, sure enough, the top of the wire is hooked up to the positive terminal. So in conventional flow, the current's going down through the wire, which means it's going to set up that flux field with the flux going that direction. So, you know, I can spin this thing and they'll continue to line themselves. Colors aren't great, but they'll line themselves up with that flux field. So that is right-hand rule number 1, that the lines of flux are going to go around the wire, and it's, you know, progressively bigger. You could call it like ripples, right? The intensity is more intense the closer you are to the wire. If I reverse the wires, what's going to happen to those magnets? If I send the flow the other direction, yeah, it's going to flip. Oh, now if I were to put my hand the way the things are, now my thumb's pointed up because my current's going up through my wire. So that's right-hand rule number 1. It's very difficult to see that, obviously, from where you guys are sitting when I try to do it in class. So this is one of the ones I highly recommend, that when you get a chance in lab, either ask me to do it with you or grab one of those and just set that up. Back to just magnets, because your homework today is going to have less to do with what I talk about today. I know it's a little bit weird, but it just gives you some timing and delay. The magnets I broke, I wrote a north and a south on them, which makes it handy. I have some other ones showing up later. If I were to take my north magnet, is it going to attract the north pole or the south pole? South pole. Bring. Sure enough, attracts the south pole. That's the north magnet. If I switch it, it goes the other way around. That's because these are free to turn, and they're going to line up with the lines of flux that are coming out of this thing from the north to the south. They are directional lines of flux. I don't understand how it works. You just got to believe us and say, yup, it sure works. So that's back to the same kind of thing. If I have 2 magnets and I try to put 2 norths together, it doesn't really want to go, because they both have lines of flux coming out of them, and it's like a head-on collision in a car. Doesn't work very well, right? But if I put the south to the north, which I think might have been how I dropped it yesterday, the line of flux from the north is going to want to go right into that south. It's like, ooh, I like that. And they attract together, and it works just great, right? So I have this magnet here. This one's super crazy strong. It's almost too strong. And can anybody see what it's labeled? Rats. Alright, so this one's north. So if I go, oh, it repels the south, attracts to the north. So here's what we're going to do. This one's really fun. I spooled just the right amount of wire on here, so that if I hook it straight to a battery, it doesn't cook everything. It's about 3 amps, and we'll learn. You could measure that. I just took a wild guess. So it's about 3 amps going through here. This will be the second right-hand rule that we learned. So I'm going to hook the positive wire up to this wire, and that wire is going around the spool this way a ton of times. So if I was going to use my fingers as the second rule, my fingers will go around here. I'm going to point it that way, so come around here this way. That would make this side, is it the north or the south side of the magnet? North side of the magnet, right? So if I fire this up, and you wouldn't want to leave it like that forever, because, well, 3 amps, it is heating up. So, you know, if you walked away, I'd probably have a fire here eventually, but that's why I did 3 amps. It buys me a couple minutes, 5, 10 minutes. So, geese, come on up here. I get nervous with magnets and computers. I'm not sure if I should, but when I was growing up, they said I'm going to erase all the games on my Commodore 24 if I put a magnet too close to them. So I get nervous, so I don't like to do the magnet ones too much over there. So which side is this? If the north, well, just point which way the north is pointing, we'll put it that way. Tiki, come on up, you can have a seat.
Wait, hold on.
The blue is north. The blue is north.
Blue's north?
Blue's north.
Yeah,
Oh, yeah. Oh, and you concur?
I concur.
Okay, yeah. So, if I could flip that up to you, you'll just have to believe them or do this yourself. The south poles are on this side, the north poles are on that side. So if you can imagine the lines of flux going through, we're going out of the north of this magnet into the south of here, through the magnet, out of the north, and you could keep lining them up. So if I grabbed a north magnet and tried to attach it to here, we said this was the what pole? South pole. Is it going to like that? It'll like it, right? Ooh, very nice. What if I take, we'll stick with the same ones, you know, I'm not pulling tricks on you. What if I take the south side and try to attach it to this side? Will that work? Yeah, ooh, very nice. It works on both sides. But if I try to reverse it, it won't stick. I'm pushing it around. It's like, no, I don't want to do that. So that's hand rule number 2. You follow the conventional current. That made this the north side. So what happens if I flip it around? Switches directions. Oh, my compasses just went wonk. And now the north is pointing this way, which means my magnet just reversed. This kind of works with this one, but this thing is way too strong. So let's see, this is south, north. It's actually going to be like, yeah, give it to me. On this side, oh, no, don't do it, don't do it. If you get far enough sideways, it'll like do funny stuff. I'm going to disconnect it because that's actually about 110 degrees. So it's warming up. Isaiah. Say what? Let's try it. Why not? So, this is made out of what? Anybody? Iron. Yeah, and we like soft iron the best. I don't know if that's soft iron, but it's iron. And we use iron because iron has a low reluctance. It's like gimme, gimme, gimme. It concentrates the lines of flux, right? So, all right, so just putting a magnet on there with nothing connected, it's still going to like it, right? It's like, ooh, I like that. So let me hook the wires back up. All right, I got to go the other way because I switched it. Okay. Now, what's going to be interesting is the moment I switch it, I don't think anything's going to happen because it's still a piece of iron, right? So I think it'll stay on there for a second. The question is, are they going to fall off or are they just going to jiggle or something? So, good question. Let's see. It's not going to shoot. It's not that strong of a magnet. So, oh,
They switched directions.
pretty cool, huh? All right. So that is which hand rule? Second right hand rule. So the way that works, if you want to go further, just come talk to me. But basically, imagine the first one we did, where you say I've got current going through my thumb, and the lines of flux are my fingers, right? Well, all we did, if you can imagine my fingers wrapping around, let's say the current, if this is the positive one, so then the current's coming this way, so essentially my fingers would be going through the middle of that spool, right? So if I have my fingers going through the middle of the spool, that's going to make this the north side of it, if my fingers are going that way through the middle of the spool. If I flip to the other side of this, now the wire's coming back around. My fingers would still be going through the middle of the spool, making this the north side. So basically all we did is we took a straight wire and we wrapped it around. We got a video later. So number 2 hand rule is pretty much the same as the number 1 hand rule. It's just we folded itself up on itself to say, oh, okay, well, which way would north be in a coil like this? Later on, we'll call these inductors, and you'll find out more why later. But, so that's number 2 hand rule. So number 1 is just, hey, where are the lines of flux all around a single wire? Number 2 is, if you coil up a wire, those lines of flux are going to get concentrated in the middle of it. That concentrated lines of flux, we can tell which is north and which is south on the concentrated lines. Amanda?
Yeah, so are you gonna go over at some point, like, we're gonna be using it in practical? I just don't get like why we're using it north and south.
You'll be using it for motors and generators. And as we go over those classes coming up, yes. So last year, well, we've had this thing forever at SMAP. And that's one of the other ones I didn't write up there yet. I'd love to get one of these like 4 times the size. So that when I'm in class, it can be like here. And you'd be like, oh, now I can see. Because when you're showing that off, it's hard to tell, right? The camera. So that's another one. If we made one similar to this, like 4 times that size, that could be fun. And if we ordered some super powerful magnets, we could even, like, we could really have some fun. But anyway, yeah, this one I had a student make for me last year. This is similar rules. It's just an alternator setup. So if this is a generator in an aircraft or a motor, this is how an alternator is going to work. So we're going to cover that later. I can't do everything in one day. So we'll get to it eventually. But I had a student make this last year, and it's like, this is awesome. Because number 1 hand rule is basically just that single wire. Your thumb is the current, your fingers are the lines of flux. Number 2 hand rule is your fingers are the wires going around the current direction, conventional, and your thumb is north or south. I gotta switch my screen.
When is it north or south?
Your thumb points north.
Thumb's always gonna point north.
Thumb's always gonna point north, unless you do electron theory. That's the left-hand rule instead of the right-hand rule.
But it still points north.
Still points north, yeah, because electron. Oh, no, we didn't get there yet. I'm in the wrong slideshow. We're good. East.
So if it's electron rule conventional, I'm kind of trying to wrap my head around, wouldn't that throw off everything if the conventional was backwards?
Well, conventional is positive to negative. We say the current is flowing from our positive terminal to our negative
But
terminal.
it's actually not.
In all reality, it's actually flowing from our negative. The electrons are flowing from our negative terminal to our positive terminal. So it all depends. Are you looking at the holes that are going from positive to negative? Or are you looking at the electrons that are going from negative to positive? So it's how you want to look at it. We'll get more into that in
Like,
transistor class.
yeah.
But you've got to decide, am I looking at this wire in conventional theory or electron theory? Because basically, if I reverse it, all that means is I've got to switch it, right? Which is convenient because my right hand is exactly opposite my left hand.
So it's not like a power outlet that has a neutron power. Like,
Not like that, no. So that's why in conventional, it's right, right, left, right. The rules all work just fine if you go to electron theory, but then it's left, left, right, left. And the problem is when you Google it and look up the history of it, everything will be backwards. Because that guy, Fleming was conventional. So when you look it up, Fleming's right and left-hand rules, and that's what we're going to hit next in a second. Fleming's right and left-hand rules are very, very similar. This looks like an almost mirror image of itself, right? So Fleming, right, right. So left is the first one. Fleming's left-hand rule is if we already have current, so we use this for an electric motor. If we already have current, so north to south is our index finger. Direction of force would be where it wants to move the wire, but we already have current established. Because remember, current, 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 induced. So third law. So that wire is going to want to go up through those lines of flux. That's Fleming's left-hand rule. Fleming's right-hand rule is basically a mirror image of it. It's just, hey, I don't have current yet, but what I'm going to do is I'm going to move this wire through lines of flux. So here's the term that's not review. This is the one I'm introducing today for you, for this. We call it cutting the lines of flux. Are those lines of flux really something you can get with scissors and, no, they're imaginary. I mean, they're there, but I don't know. It's a theory, or whatever. If you sprinkle pixie dust, they'll show up. Or iron shavings, one or the other. So, on Fleming's right-hand rule, if we move the conductor, if we cut the lines of flux, it will generate and you can either say voltage or amperage, and we're going to deal with that today. So in the right-hand rule, I point from north to south with my index finger. I move the wire, still movement is your thumb, and one of the ways I remember that is if you need a ride, you know, you guys don't hitchhike anymore. But if you need a ride, you need to go somewhere, the movement is your thumb. Hey, I gotta go somewhere. So movement's on thumb on this one too, right? It's the direction of force that the wire wants to move. This one is the direction we're already moving it. And if we do that, there's a direction that we're gonna wanna induce the current to travel. We're gonna make a voltage, a forcing. So they're pretty much the same. So if you switch from conventional to electron, all we gotta do is we flipped it. So you'd be like, oh, now it's Fleming's right-hand rule is for motors so as long as you understand that. So we got 4 rules. 1 is just the right-hand curl for one conductor. Number 2 is the right-hand rule for a coil. Number 3 is the left-hand rule for a motor, and number 4 is the right-hand rule if you want to generate the electricity. So we're going to go over this a lot, and that's why I highly recommend playing games when you see coils, when you do stuff like this. As we get into even voltage regulating class, this will get important because we'll wind the wires. Who's asking me I'm practical? We'll literally, well you won't, but the manufacturer will wind the wire a certain way around the core, and then that will either fight against or help the magnetism of either another coil under it or a magnet under it. So you got to know, well, which way is it wound around there? So that's where it gets super practical, other than the motors. Shane?
On the left-hand rule, do we also talk about cutting the lines of flux, or we don't because we're not moving the wire?
So the left-hand one, we're kind of assuming that it's not cutting the lines of flux at this level. What's going to happen later in life is we go, oh, well, I'll put it this way. Do I have a motor up here? I'll grab a motor.
The right one's cutting because we're actually moving the wire.
Yeah, I got a motor for you. I will say, well, at least I got part of a motor. So if the motor's not spinning, I could have done this one, I guess. If the motor's not spinning and we just put power to it, it's going to go pretty high amp draw, and it's going to try to spin it, right? So it's going to try to spin this. Once it gets up to speed and we're spinning really fast, now we are actually cutting the lines of flux, and guess what? Opposite effect going on. So we'll have a lesson about that being Lenz's law. Lenz is a guy we'll talk about later that said when we cut those lines of flux, it produces a back EMF. So if you get that motor spinning fast enough, the speed of the motor actually counters the voltage you're putting into it, and all of a sudden it's not going to go any faster anymore because, well, yeah, but that's not this lesson. So if I lost you there, just forget I said that. But yes. All right, I added these to slideshow 1 for you. That's kind of our review. So yeah, if you were a little lost, I half expected that yesterday. Part of it was, this probably should be more like lesson 4 or 5. But if I hit you one time on lesson 4 or 5 and you're all as confused as you were yesterday, then it takes me 3 days to get you where I need you to be. So kind of an intro there. We're going to do our dances, right, left, right. We're going to get them memorized. We're going to see it and stuff so that by the time you actually need it, if I can phrase it that way, you'll be like, yeah, that's no problem. That's pretty easy. Okay. If you want to read along with today's, we're in chapter 12, page 12 to 20-ish. We're going to leave behind some magnetism stuff, with the exception of, if you look at your lab, I think I have lab 3 on your lab timing schedule. So lab 3 is basically all about those magnetism we were talking about. So after class today, I wouldn't do it while I'm talking. After class today, you're welcome to start on lab 3. It's going to be a lot of that magnetism, the hand rules. And we'll move most of this stuff out so you can play with it as well. Did you have a question, Joe? I got a joke about you. Sorry, you got a question?
Yeah, when you want that brief finished by, roughly?
The exam. When do you want if you have them done, let's say a day or two after what's on your calendar I gave you, you're on pace. So, I mean, you can do them out of order, it just won't make a lot of sense. That calendar is mostly to say, hey, this keeps you on pace. Like, the way I would phrase it, this isn't a third grade class, where I'm like, well, okay, I shouldn't say that, because Ryan's classes, sometimes they're more strict. But, in my class, if the labs are done, when the exam's done, I'm happy, like, no problem. Some people, I don't like this necessarily, some people will actually do them and not hit submit, because as we learn more, they'll be like, oh, that's what they meant. And they'll go change their answer a little bit. So you can get a little bit better grade if you don't submit the labs, but it's done. The problem is then the 2 days before the exam, I got a lot to grade. And it backlogs me a little bit. So if you can kind of read between the lines there, you don't necessarily have to be a rush to submit them. But the flip side to that you're going to want to manage is if you wait till the end of class to submit it, hit submit, you get a terrible grade. I didn't have any time to come help you understand it. So there's a balance between turn it in, if you have wrong ones, we can talk about it, or don't turn it in because you might tweak it later. So you gotta figure out in your own life where that balance is at. Okay. Sorry, my tough guy joke. Job, no, it wasn't Job, he's good. This guy walks into a bar and, I don't even know if Job drinks, but I'm not gonna ask him in public. A guy walks into a bar and says, hey, I need a drink. It's a dry bar, so it must have been a ginger ale. And the bartender says, we only serve tough guys in here. You don't look that tough to me. And the guy says, I'm tough. The guy goes, I don't think so. He goes, I'm tough, really, I'm tough. The bartender says, prove it. The guy said, well, I was working in the factory, and on one of the machines, I got my arm ripped off. He had 2 arms. The bartender looks at him and goes, what? Yeah. He goes, that's stupid, not tough. He goes, yeah, well, I sewed it back on myself. The bartender says, wow, that is tough. That's so tough, I'm going to buy your first drink. And the guy goes, cool. Love that joke.
I heard it was sharp.
Cool, a shark bit it off. Well, you're from Florida. All right. So, yeah. This is where we're going to start today. These are basic circuits. I think I have a slideshow somewhere that says that word circuit. You should understand what circuit means. Circuit is a complete path. It goes all the way around. If you're going to run a race circuit, you're going to run the whole thing, right? So these are circuits. They go from a power source all the way through the electrical load to the circuit. Now, some of these circuits are not, I'm going to use the word complete. That'll come up later. If the switch is open, the electricity can't go all the way through it. So the switch technically would have to be closed to be a complete circuit. And we're going to talk about what open and closed means a little bit later in the lesson. But these are what we call circuits, electrical circuits. If you have a battery and you hook this whole thing up, maybe you want to make a magnet and you hook it up to one side of the battery and it's connected to a wire, and out the other side of the wire you've got your jumper wire, but it's not connected to the other side of the battery, not a complete circuit because it can't go the whole way. We would call that an open circuit, and it can be open in a bunch of different places. So these are circuits. Our power source could be a battery, it could be a generator. We even have power sources that are made out of all kinds of other things. We'll talk more about that, I think lesson 6 or 7, when we talk about power sources. So these are electrical circuits. One of the main words we need to learn is volt, or voltage. You guys don't have your book that I had that they moved. Shoot, Dale Crane. Anybody have it on their computer? Yeah, that dictionary, Dale Crane. It was right here, wasn't it?
I've got a copy.
I got a copy too. I gotta get this because it's so important. I'm gonna grab, you got one? I got one right here. I'll be right back. Sorry about that. When I prepped this class, there was one on the front table. They had some thing yesterday and apparently cleaned off everything. So, some of the definitions, especially the important ones, I like to look up right in the definition book from Dale Crane. So I'm looking for volt, V-O-L-T. There's a lot of V's, that's surprising. Alright, volt, right there. Zoom in. There we go. Volt, electrical unit. The basic unit of electrical pressure. So what you want to memorize is pressure, 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 pressure. Feels like I have this highlighted in my book, so maybe I stole somebody else's. But, basic unit of electrical pressure. Now, it'll go on to say 1 volt is the amount of electrical pressure needed to force 1 amp of current through a resistance of 1 ohm. Well, we don't know what an amp and an ohm is yet, so we're going to keep going and I'll tell you that. But a volt is pressure. It can be very helpful to think of voltage like pressure in a water system. For the most part, if you have problems with electricity and understanding what's going on, you can switch it over to picture a wire being like a water pipe. And you guys use so much water in the real world that it'll start making better sense in your head. So a volt is like how much pressure you have trying to push water through a pipe. So if you had a pipe that you were trying to push water through, but it was shut off, there's a valve that says you can't go through there, you're going to still have pressure in your pipe, but it's not doing anything because the valve's shut off.
The way you're explaining this, are you talking electric flow now?
Either way works. It can be holes or negatives, but I always speak conventional unless spoken otherwise. So I'll always tell you in conventional unless I specify. Conventional is plus to negative, positive to negative. Yep. It works the same way in reverse. It's just you got to use the other hand. Yeah. So voltage is pressure, and what do we know about pressure? I haven't talked to you too much about pressure yet. Hopefully Christina did. If I picked one point in space, can I tell you what the pressure is? Not really, because pressure is a difference between two things. So if I picked one point in space, I could tell you what the pressure difference is between that and something else, absolute zero, space, atmospheric pressure. But I always need something to reference, right? Pressure only works with 2 reference points. So kind of. What you were thinking was, well, in reference to a vacuum, you could.
It's space, there's nothing in it.
In reference to space, but you have to have space to compare it to, right? So pressure is that. You always have to have 2 things to compare it to. So with a battery, we're comparing what the pressure is in the positive, trying to push out, to the negative, trying to draw in. And we just look at that whole picture and say, a typical battery like this is 1.5 volts. Don't memorize that number. That particular battery is 12 volts. So the pressure difference between this side and this side is the voltage we have. So it's the pressure difference between 2 points. So you always need 2 points to measure a pressure, which means you're always going to need 2 points to measure a voltage, because I want to know the difference in pressure between 2 points. And it's the pressure that pushes the electrons through a wire. Or conventional flow, you'd say that pushes the holes through a wire, but same thing. It works the same idea. So voltage is pressure. Resistance is measured in ohms. Ohm. So an ohm is a resistance. Now you can either use circular reasoning or just memorize these. 1 volt will push 1 amp through 1 ohm of resistance. And we're going to do the math and show you that all later, so don't worry about like getting that in your head. But resistance is measured in ohms. So if you're thinking water flow again, or a hose, if you've got a really, really long hose, is there a lot of resistance to flow there? Yes. So if it was like water, you'd say there's a lot of ohms in a really long hose. If it's a huge hose, is there going to be much resistance? not much resistance to flow because it's super easy to push through a big, huge, when I say huge hose, you know, big diameter hose. So, volts is pressure, ohms is resistance. I have a note here, and if you're following along, because I think the PowerPoint's open, number 2. Later in this class, we will switch ohms from resistance, the total resistance of a circle, so we'll switch it to saying impedance. I don't necessarily need you to memorize that one right now, but just know it's coming down the track, because if I use just the word resistance, technically when we get further along, we are talking simple. Once we start throwing capacitors and inductors, which you guys don't know about yet, into the equation, they mess with the total resistance, and then we're going to switch that word to impedance. But for now, resistance is what is holding back all our little amps. See how I did that? Holding back all our little amps. So I like to use resistance is ohms, and we'll add to that later. Ohm's law. So this guy from Germany, George, is it still George if there's no E? George Simon Ohm. He was the one that basically, I don't know if he did the math or he just invented the numbers. So he decided that 1 volt of electricity will push 1 amp of electricity. So 1 amp, does anybody remember how many electrons are in an amp? Yeah, 6.28 billion per second. So he said 1 volt will push 6.28 billion electrons per second through a circuit that has a resistance of 1 ohm. So he got to name resistance after himself. Ohm. So that's the guy, right? I don't know if he could count to 6.28 billion at that point, but you know, it happened. So maybe he was just using columns, because I have a problem with that word, C-O-U-L-U-M-B. 1 amp is 1 coulomb of electrons per second. If you thought of a bunch of army guys marching in a line, you might say, oh, that's a column of army guys, right? That's how I remember it. So 1 amp is 1 coulomb, which is 6.28 billion guys marching per second. So the way I think of it is, think of 6.28 billion little ants, and if we have a 1 volt pressure difference, it will push 6.28 billion. You don't have to memorize that, but I think it's going to happen this year. It's actually 1 coulomb of electricity per second through that 1, and this is how we write ohm, 1 ohm resistance circuit. Is that an omega, I think? Omega, ohm. So, that's the simple math for the 3 terms that if you get this, and we're going to do some more math later, if you get this, you'll be able to pass your writtens with about an 80%, maybe more, with all these, even if you forget the hand rules. So the good news is, it's super easy math if you're like, oh, that's not so complicated, I can figure that out. So I like to say ants. You'll hear me say ants a lot, because I'll say, how many ants did it push down that wire? Because remember with our candy, it passes it kind of one to the other, but if you take 1 point in the wire and count how many ants went by, how many coulombs of electricity, that is your amperage. So AMP is the word. AMP. It's an ampere. They shortened AMPERE. So 1 ampere is 6.28 billion electrons per second. We usually just shorten it down to amp. So if you don't know if I said amp or ant, it's because I do it on purpose to try to kind of cement it into your head. How many amps do we have? How many ants did we push along the circuit? All right, you guys all following me? Cool.
Would it be inaccurate to say that amps are the amount of electricity and voltage is how fast they're going? Like in a simplified way?
They're going at the speed of light, so you couldn't do that. The amps being the amount would be correct. but it's an amount of electrons, not necessarily the amount of work we're doing. We're gonna get to that.
Okay.
So yes, amount, if you were gonna count each individual electron, amps are the amount. You are right. Shane?
Voltage being negligible, how many amps does it take to kill you? Like point.
It doesn't exactly work that way. It's kind of complicated. Depends where it goes through and,
It's shockingly small.
yeah.
Oh, sorry.
That was not on purpose.
See what you did there?
It's something like, it's something like 0.3 or something.
Yeah.
Kill you.
I've had 50 amps go through my body and I'm not dead yet. So
Did yet?
if you put it through the right spot, it'll kill you. Cross your heart. If it's not going through your heart, well, you might end up like me. I've been shocked lots and I haven't noticed any problems with me. Not to mention, I've been shocked a lot. I ain't noticed any problems with me. Alright, currents measured in amps. We shorten the word to amps. Amperes, amps. 1 amp is 1 coulomb per second, 6.28 billions. That's a lot of little electrons. Alright, here we go. Here's the math that Ohm came up with. 1 volt will push 1 amp of current through 1 ohm of resistance. So here's the formula. But why do I have funny letters here? It's because nobody can agree what letters to use. So you guys get to memorize lots of letters. E, we're going to go to the next slide, ends up being volts, and I'm just going to switch slides. But volts equals amps times resistance. Y is amps and I. You'll find out in a second. A couple different languages. So, with Ohm, he was, I think, German. And for voltage, he used electromotive force, basically. So, electromotive force, kind of sounds like pressure, right? Force, pressure. So, your pressure is your volts, or your electromotive force. So, if you ever see EMF, electromotive force, what they're talking about is voltage. They're talking about a pressure. And they will use E mathematically in a lot of your physics. So if you see that capital E when we're doing electrical math, that means your voltage. So I have a slide coming up. If I don't have a slide, we write them all up on the board so that you're like, why do I got 3 different letters? Like, well, because if you didn't, then people that don't have an AP could do this. So E, electromotive force. I'm bad at math. If I know my amperage though, let's say I have 2 amps, and let's say it was 5 ohms of resistance in that circuit, how many volts did I have pushing that through there? 10, that's right, that makes it easy, right? So okay, that's fun. Easy math, that's a whole homework, just doing that math. Okay, but what if my volts are 8 and my resistance is 2? So now I got 8 and I got a 2 and I don't know how to figure that out, and I hated this in math class. So you'd have to divide both sides by 2, right? So you turn that formula of 8 equals, we don't know, times 2 into 8 divided by 2 equals, we don't know, times 2 divided by 2, which equals 4 equals I. Current. How many of you guys hate that kind of math? Just show your hands. It's okay. I see you, brother. I see you. All right, I hate that math. I can't. I'm not going to do back in 4th grade where we're going to make you show your work longhand, because I couldn't get there. I would be like, I know I got an 8 and a 2. Let me multiply them, divide them, and do it a couple different ways until the number looks right, and I'll write that down on my paper. That was me. So, I came to SMAT, and SMAT gave me a cheat. I love cheats. It's like a cheat code. No, it feels like you're cheating. I gotta double check something a minute, because I don't want to skip too far ahead. Alright, good. $200 years ago is all. 1827. Isn't that crazy? So only 200 years ago, this guy came up with this, and it changed the world, basically. To me, that's unbelievable. That it was only 200 years ago. Anyway, so we can do the math in those circuits. We're going to do them in a minute. Here we go. Here comes the cheat code. There is your cheat code. We draw a triangle. Inside that triangle, we put volts at the top. We put amps. That's a big M. And we put resistance. Now we could relabel these a bunch of different ways. I just realized I drew it way too small, so we're going to do it again. So, all right, volts, amps, resistance. All right, so you already are going, why did you write that? Why didn't you write something else, right? But that's the triangle. I'm going to show you how to use it, and then we'll fill in the boxes. But, well, no, we'll fill it in first. What else could we write up in there that's the exact same thing as volts? Just, you know, E, we could put an E up here. We could put an EMF. Volts, E, EMF. That's pretty much, I think, the only thing we introduced. How about in amps? We've got I, or we have current. All three of those mean the same thing, right? And over in this one, I wrote resistance. That's nice because it's often an R. What else could we put? Ohms. Or we could put the omega sign. So there are 3 or 4 options that you could draw in there that all mean the exact same thing. You just got to figure out which one you want to use. And or you figure out which one the person that's asking the question is using to make sure you use the one they want, right? So here's the cheat triangle. Here's how it works. If I know I and R and I want to find out E, that line between them is just multiply. So if I've got 2 amps times 4 ohms of resistance, that line is multiply. 2 times 4 will give me 8 up top. What if I know my 8 up top, but I don't know my resistance? Anything down below this line is divided by. So if I put the one I know up top, 8, and I know a 2 is under it, 8 divided by 2 equals 4. So use that triangle for that super simple math. Some of you guys that are good at math are like, I didn't need that cheat. And I'm like, this is the most amazing cheat ever. So this is the triangle you absolutely have to memorize. E over IR. Fill in any other words you want. You can use whatever word you want. But as long as you have this memorized, that volts are E, EMF, we could say pressure if we wanted to. Now you can do all the math for 98% of any math question anybody's going to ask you in aviation. There's about 2% that we're going to spend a bunch of days getting the rest of the math figured out. But for the most part, 98% of your math can be done in this triangle. Okay? Any questions on the triangle? Pretty easy? Okay, so we're going to be playing around with that triangle an awful lot. On your homework, when you have them, especially on Moodle, one of the tricky parts with it is you'll get a diagram. You'll get a diagram that'll look something like this, and instead of a light bulb, maybe they'll have a ziggly-zag. That's the symbol for a resistor that we didn't learn yet. And then they'll say over here, they'll say that's resistor 1, and it equals however many ohms. And then they'll say, what's the amperage for number 1? And they'll say, what's the voltage across number 1? We're going to get that in a little bit during the slide. Usually on the left side, but they'll also give a RT, ET, and resistance, volts, current, in whatever order. So total means you could say the total circuit, or you could say what's going in and out of our battery if we want to phrase it that way. What I do is I'll do a little triangle at each one when I'm learning, and I'll just plug it in. So if they tell me the voltage is 12 and they tell me the current is 2, all I gotta do is divide 12, it's over the 2, 12 divided by 2, that's gonna give me a 6. So I'd put 6 in that one, current was 2 I said, voltage was 12. So if I know any 2 of the 3, I just fill in that circle, or the triangle, and away we go. So on Moodle, it's on your computer. I highly recommend using a scratch piece of paper. Solve the whole problem they have, all the answers, and then once you have it solved on paper, you're probably going to get 3, 4, 5 questions in a row on that same exact diagram, and it'll say, what's resistance total? What's resistor 1? And just have the sheet there. Originally, this is the first year that we had these on Moodle, and I was like, this is not good. They're going to make a ton of mistakes, because they're going to get the right answer, but they're going to get confused between, they're going to look at RT when they wanted to look at R1, and they're going to put the wrong number in. So originally I was kind of like, I don't like this. We're going to mess up. And then I got thinking about it, and a huge part of aviation maintenance, bigger than knowing electrical, is knowing how to transfer numbers around. So I was like, oh, well actually, if I give them enough lab time, it's very good practice for not putting the wrong number in the wrong spot. So think of it that way. Yes, a lot of your labs that I have an hour down on how long it should take, you could do in 10 minutes if you were like a math whiz. But take time, draw the thing out on a sheet of paper, fill it all out, and then slowly put them in. And one step beyond that would be, before you put them in, and we'll see it later today, make sure the math works for the whole thing. And you don't quite know what that means yet, but we'll cover it shortly. Check, check, check. All right. I think I got, let me double check where the break comes up. All right, we're getting close, yep. Very good. One last thing that we're going to introduce today is power, which is watts. So let's give ourselves a circle. I'm going to give it a battery with a plus and a minus. It's going to go through a resistor. Yeah, that'll work. And come back to my battery. It's a complete circuit. Let's say I've got 6 volts at my battery. And let's say our resistor is 2 ohms. How much current am I going to have? So it's 6 volts, 2 ohms, 6 divided by 2. I'm going to have 3 amps. So I can just write in here somewhere 3 amps. All right, that's pretty cool. We solved the problem. Now, one extra thing is power. So if I turn the pressure up really, really high, if you get hit with 6, well, we'll use this one. If you get hit with 3 amps coming out the end, it's going to hurt a lot more coming out of a higher pressure gun, right? Basically. So power, or the amount of work we can do, what you do is you take your voltage and you multiply it by your amperage. So our power is in watts. There's a guy named Watt that came up with this. He followed ohm shortly. And he said, oh, okay, well, the amperage itself is not how much work we're doing. It's actually the amperage times the voltage is how much work we're doing. So in our triangle, you could make the same kind of triangle. And watts, which is power, would be above volts times amps. So I don't want to give you too many triangles. That's kind of the last one I give you. And this one we reserve for when you have watts. If you have a 100-watt light bulb, you generally know around here we're at about 100 volts out of the outlet, right? So it's going to be using 1 amp. So that's how I remember it, is I go watts. Okay, how many watt light bulb, how much power, how much light is coming out of it? It's the volts times the amperage. So that's watts, that's power. If you really are into physics, which I'm not, you can convert watts over to a watt is 1 joule of work in 1 second. If you're into horsepower because you like engines, a watt is 100, not 100, it's 1/746 sixths of a horsepower. So that means how many watts would I have 1 horsepower? 746. That'll come up later. We'll ask questions about, you've got a motor, let's say you have a motor that's 100% efficient. None of them are, so we'll do that math later. But if you got a motor that's 100% efficient and it's using 1,400 watts, about how many horsepower is it? About 2 horsepower. So real rough math there. All right. They came up with this table for you, and I'm showing it to you. It's in your book. Usually your O's and P's are open book test. This one I do not memorize. I just memorize those 2 triangles. Basically, this is the one triangle we memorized right here, right? E, I over R. They like to throw the power one in. That's the second triangle I had you memorize, and it works. If they don't give you all those numbers and you don't want to do the math, you can go to this one and you can say, well, I know my power and I know my voltage. I want to know my resistance without knowing the amperage. Basically, you're just skipping a step. I don't really like this one because you're skipping steps. You might not know how you got there, but it exists. The only one in here that's kind of fun is you could say, well, how does power equal I squared times R? Well, basically, if you had our original triangle where volts is up here, amps is here, and resistance is here, if I know my amps and my resistance, let's say it's 2 and 3, 2 amps times 3 ohms of resistance would give me 6 volts. And if I said, well, how much power is that? I would have to take that 6 volts times 2 amps to give me 12 watts. I just did the math twice. Not a big deal. It's pretty easy. You could just come right down here and say my 2 amps squared times my resistance is going to be my power. So 2 times 2 is 4 times 3 is 12. I'm showing you it because it's available. It exists. I don't use this. It confuses me, but it's available and it exists if you're into doing it that way. I would rather just do it in 2 steps.
What's the second triangle?
Watts is volts times amps. Okay. There's the 2 triangles for you to answer your question. Power is current times, whoa. Circles work too. That's the same thing. All right. There's your 2 triangles. Voltage is current times resistance. That one you got to remember. It's E, I over R, E over I times R, where the watts one is power is I over E. You could say pi. All right. We're going to take a break and then we'll run some numbers. Okay. Let's say quarter after. Come on back at quarter after. I'm going to turn the air on. Is it getting hot in here?
It's on.
You guys said no. Go grab another sweater.
Count. This is -6. Concentration -6. So I would move, that would move six places, right? That's what I figured here. Now, can we count the 0? You're starting from the decimal point, not decimal point. Oh, well, yes,
Yeah.
okay.
I want to say
So
two.
6 places. I'm gonna make it for the
-2 electrical
every
symbols.
one of these
Okay.
is moved by 3 zeros.
Yeah, we haven't really gone over it. If you look at your calendar,
With micro.
I don't have you doing that for another couple days. We did, which you're welcome to do.
What's the total of this one right here? Yeah. So you have 300 plus the 6 on the micro. How many is it? 9. 9. So which one is it?
say we have it hooked up, do that one.
Isn't this real serious?
Yeah. Let's say we have it hooked up that way. Is it a magnet right now? You didn't see that.
I didn't see that.
Which side's north? And how do you determine that?
You ever, right?
We're going positive,
Oh, black is your positive?
well, positive terminal.
Right, okay. So I feel this way and it's, that's your new list.
This is the north.
Yeah.
Isn't that cool?
That's so cool.
So if you switch them,
How would you know how far to move this though?
I like that. It switches. So now we just switched. Now we're going that way. And it's that way. And if you can picture in your head, grab one wire, if you will,
Wrap around.
and wrap around just that wire. And then you say, well, what flux is gonna be going through the core when you do this? And the direction's going the direction of your finger. So now the flux lines of that are going this way, right? Through the bar. Like if you could replace,
If I'm, say like I'm grabbing this.
you grab the top wire or the bottom wire? So let's grab this top, let's grab this top wire,
Okay.
right?
Yep.
And basically, your middle
'Cause I'm
finger would
pulling.
be the bar now, essentially, right?
So I'm pointing this way. With my hand, right?
Well, you'd be pointing this way above the wire, but below the wire, which is where the bar is, your fingers are going that way.
Oh, cause I'm curling.
Cause you're
Okay,
curling,
so
yeah,
it's-
'cause it's
okay.
around and around and
Right,
around.
right.
So if you just grab that one wire and say the lines of flux that are now cutting the bar, they're going through the bar this direction, right, with your fingers, which means south to north in the magnet itself. So that's why it makes it.
I do remember.
Because we're stacking up the flux from this wire and this wire and this wire and this wire and this wire. Because if you were to switch that around and grab a wire that's down here, that one is going that way, right? The bottom wires. And if my fingers were essentially going through the middle of that, they're still pointing that same direction. And here's this, so it's the same, but
Right. Right, okay. So if I then have that right
Yeah.
next to it.
if you reverse it, they'll switch.
Depending on where you're going, if it's asking for like a micro and a pico,
So it switches, okay.
taking
Yep.
a micro to a pico,
So if you disconnect it totally,
and then add that right here.
it's like, one's one way, one's the other. Normally that works. There might be another magnet sitting around here.
Wait, this thing.
It might be. They're pointing out the directions. Did we screw up a magnet?
Something I heard. Yeah.
This one's actually very strong. It might just be that we had that. Look at that. We magnetized the magnet. That was no longer work. Tracks the south side, tracks the north side.
Nice.
Okay. Good thing I got them on order. Huh, let's see, this is south, we have determined.
Yep.
So this one's correct on here. This one,
That one's wrong. That one's right.
no, this is the wrong one. The south is silver.
Oh,
I got
right,
two
so
souths.
there's two souths.
That one's incorrect, that one is correct. That's wild, so we actually, so part of how we might have done that is putting a magnet in a field and charging and discharging. But what I might be able to do is,
5,000 amps equivalent to 0.005.
so I actually have to read,
This would be, it would be 5.
Take it apart.
I got the wrong units.
that's wild. I is positive would make
Yeah,
it the
I think you just got the wrong units.
north side.
Because I need to go first, 1, 2, 3.
It's just backwards. I don't know how to fix it.
So,
Well,
way
I was-
bigger than
If we compass.
It's because I said it was wrong, I hurt his feelings.
Yeah, it changed to what I heard.
Yeah.
We had it in a magnetic field and we were powering it up and down somehow. So this one still works.
Yeah. You ready?
The north points towards the south. This one, the south points towards the south, so that's no problem.
We went along with the theme of breaking stuff with the other ones.
Ready?
Next time I need to know how much
Ready? I think I got it.
stuff to
Did you?
plug into the generator.
Ta-da!
How?
I went underneath and I spun it.
It was like unscrewed itself, you think?
Oh wait,
Take the wrong one out?
this is correct.
That one's right.
That's wrong. Shouldn't. No, it's right.
Alright, we'll see what he says. Well? See again.
No, it's right. Okay.
That works.
All right, we're back in the good. Okay.
So just take it underneath and
Well,
spin it up.
so imagine we got the flux
Yeah.
lines. When you spin it, we're cutting that magnet with a bunch of lines of flux. So that's part of how we made magnets. We had it too close to this when we were going on, off, on, off, on, off, and one of my compasses was remagnetized in reverse. So there, we're back in the good.
I'm gonna give it like
All right, so if we're back in the good, I guess we gotta come back.
these things look like you got it out of like one of those survival washes.
That's north, right?
We might still be too close.
So this is how an alternator works.
Is that a bit
All right,
Having a magnet.
that's why we need to put it on a wooden.
Somebody
base.
smart.
All right, we're back.
Why wouldn't you use an alternator on a generator so you can spin it forward?
How many?
That's got alternators on like
I think that's pretty good. Do unit and measure?
That's great.
basically what own.
Kill the tiki sounds kind of violent.
That's what George Hill did. He was like,
Well, part of it, our house, we're
I
doing
don't
AC,
think I wanna kill the
which is all we need.
Well, depending on which team. I'm not the only team.
We're talking about DC current, assuming all our answers is going running one direction down the wire. Eventually, we'll switch over and we'll start talking about
vibing with this electricity.
We will be when we get to AC. That'll be more fun. Okay. So, we're gonna do a little bit of math here. We're gonna draw names out of the hat. We're assuming this switch is closed, so I got a little bit of a definition to go with. The reason they say closed and open is a little bit weird. It's reverse of what most people would think. This is a switch. It kind of looks like a gate, like to your yard, right? See how it looks like a gate to your yard? And when they named these, a moron named them. I don't know who it was, but they named them. Does this gate look open or closed right now? Open. Yeah, that's an open gate. Unfortunately, an open gate does not allow electricity through because we're trying to get our electricity to go from this point to that point. But is there an electrical connection there? No, it can't get through. So an open gate means there's no electricity going through it. Oh, that hurts a little bit, right? Basically, they want you to see that picture of a switch in your head when you think open. So if we were to close this, now I could draw it with that switch laying right on top of there. That's now closed. Now electricity can travel from point A to point B through our switch. So this is a closed switch which allows electricity through. A lot of our drawings on my PowerPoints, for some reason I ended up with open switches, not allowing electricity to go through. So I try to, when I catch that and I'm talking to you guys, I'll just go in here and I'll connect it with a line, causing it to be closed, just so you know. T.
Picture it as a drawbridge instead of a gate. The drawbridge opens, he can't get across, drawbridge closes, he can get across.
Oh, I like that. It's a drawbridge.
I've been struggling with this for years, but I'm getting it.
Wow, I gotta write that down actually. We're gonna add that to next year's PowerPoint.
Oh, yes. No ATVs and droppers.
Huh. Back to that Florida girl. Okay, so if this was closed, we're assuming it's closed now for our math, because if it's open, there's no amps going around, there's no amps, there's no electricity flowing, because it can't get through. And for the most part, for all of this math, figure complete circuit, like remember we talked a little bit about static electricity a while back? Static electricity, we're just gonna forget that. Like, it doesn't exist anymore. When we're doing math with electricity, static does not exist. So you don't have a bunch of people piling up at a point here or there. No, we don't. We just ignore static electricity because there's not 6.28 billion electrons going through with static typically, so we don't really care. So if that's closed, we'll give ourselves a battery. Let's make it 10 volts in this instance. And I didn't touch on yet AC versus DC. We're talking DC current so far. DC means direct current. When we get to AC current, that's alternating current. Alternating current means first all the ants are on one direction, and then they turn around and they run the other direction. And then they go back and forth and back and forth and back and forth and back and forth. We will get there eventually. The math still for these things we're doing with just a straight up resistance, the math still works just fine with AC or DC. But when we get there and start talking impedance, it gets a little trickier. So for now, we're just going to be talking we're just going to be talking DC current, like what comes out of a battery. But if I wanted to make it AC instead of a battery, a lot of times we'll draw something like that. It's a alternator. The math still works, so I could do that. So just so you know, but we'll get to that eventually. So 10 volts, whatever kind of current, I don't care at this point because we're at elementary level. My light bulb, we're going to say is, somebody give me a number for resistance. I heard 20. 20 ohms. So if I got 10 volts and a 20 ohm resistor, how many amps am I gonna, don't answer, how many amps am I gonna have? David White. Usually when I do this, I draw really slow, so if they don't come up with a number, they're like, 0.5. Let's see how we got there.
Yeah.
0.5. So 0.5 amps. All right, cool. All right, let's change our number. I heard somebody say 12 at one point, right? So we'll stick with our same 10 volt battery. Looks like it's going to be Mike, just because I like you today. Mike, I have 10 volts and 12 ohms. How many amps am I going to have? Say that a little louder. You might be. Is that right? 10 divided by 12.
That's 0.8.
You did 12 divided by 10. So 10 is over the 12, so 10 divided, I don't have a calculator. 0.8? 0.83 repeating. 0.83. All right, everybody tracking us so far? All right, so we're going to do one more. If you're totally lost, you shouldn't be, so get caught back up at break or something. So let's say I've got 10,000 volts. Probably not a battery. And I've got 2,000 ohms. many amps am I gonna have? We could have done 10,000 and 2,000. 5. Right?
Fine.
Yeah.
Yeah.
5. 5. Because 5 times 2,000 equals 10,000. So, you know, depending on where we throw those K's and whatnot, you gotta be careful how that works. Alright. Does anybody, other than James, that was a tricky one, James. Does anybody not get it? Because I'll give you another one, you can do it. Alright, good. You guys are all getting it. Alright, so we're going to move on because we're going to do similar, just a little bit more complicated. When we have resistors in series, resistances in series, the cool part with this is they add up. Kind of makes sense, right? Think back to hoses. If I got a 100-foot hose and I add 2 more hoses that are 100 foot long, I'm going to have the same amount of resistance as how long would the hose be? 300 foot long. So if I throw in here a 2 ohm and a 2 ohm and a 2 ohm, and then I ask the question back here, I say voltage total, resistance total, amperage total, and I'll give you the voltage, let's say 24 volts. I go, oh, I don't know what the amperage is. I'm going to have to figure out my resistance first. So we can add those up. 2 plus 2 plus 2 is 6, right? It sounds simple until you're in front of 30 people. So 6, so my resistance total would be 6 ohms. Well, now I have 2 of my 3 in the triangle, so I can take my voltage total at 24 volts. I can put my resistance total down here. 24 divided by 6 is 4. So I'm going to have 4 amps. Hey, that's kind of cool, huh? So everybody tracking with us? Alright, so this guy came along named Kirchhoff. Is there a Kirchhoff Center? I have the wrong name. It is Kirchhoff. Doesn't Grand Valley State University have a Kirchhoff Center? Nobody knows. Alright, it's in Allendale, about my backyard. So Kirchhoff came along and he said, hey, that's kind of cool. Because this was our total, right? And I can add them up. He said, I can figure out that if I simplify this thing, we can play some game with math. So Ohm figured out the basic one. Kirchhoff came along and he said, this is fun. So I got 2 ohms of resistance. I know I have 4 amps going through it. So I can make a little triangle there. I don't know what my voltage is, but I know I got 2 ohms. And I know I got 4 amps. 4 times 2 is what? 8 volts. Let's do that one here too. Oh, that's going to get boring, isn't it? So, still going to have 2 ohms of resistance. If I had 4 amps that went down the road, Kirchhoff says none of them get lost. That's the cool part. Kirchhoff basically said no amps ever get lost. That's actually what the law that he wrote was. If you try to read it in a book, it makes it look like the voltages don't get lost. Well, how does pressure get lost? So if you think of it like the amps never get lost, it's easier to understand. So if I have 4 amps, which I'm simplifying because I don't want to do 6.28 billion times 4, and the number is too big, right? So I got 4 amps going through this one. Well, guess how many amps are going through that one in a closed circuit? Because it's only one road. They don't have any other ways to go. So there's 4 in here. 4 amps, so 4 times 2, 8 volts. And now we could do the math down here, or we could do different math. And Kirchhoff would say, well, our amps never get lost, and that means out of my total circuit, the total voltage drop across all my loads in series is going to have to equal what we started with, 8 plus 8 plus, it's all 2, so if we did another one, we're going to have 8 volts with 2 ohms, 4 amps. And I feel like I almost almost made that too simple. But so basically Kirchhoff said our amperage through a circuit, whatever leaves my battery, has to come back into my battery. That's basically Kirchhoff. He actually made it quite a bit more complicated with a transistor, and we'll get to that later. And he's saying I've got amperage coming in here, and out here, going back to a battery. And he's saying, well, whatever goes into my battery has to be what's coming out of my battery. So it's a little bit more complicated than that, but we'll cover it later. So without confusing you, back to just the simple version. Whatever leaves my battery has to come into the other side of the battery. So it makes the math super easy. So Shane, go for it.
No, we're not saying that we've got 24 volts at the first resistor and then only 16 at the second and then 8 at the third. We're not saying that. That's not true.
That would be inaccurate, because whenever we do volts, we need 2 reference points. So let's give ourselves another set of numbers. Let's give ourselves 100 volts. And we'll make this resistor 10, this resistor 5, 15. I'm gonna go with 5. Trying to make it so the math doesn't get too wonky. All right, so that's ohms, 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 ohms. So 100 volts, what's my resistance total? Oh, I saw Shane's face. Look at that. Total resistance, Shane?
20 ohms.
20 ohms. 10 plus 5 plus 5. Now this works in series. We're going to do what we call parallel later. So 20 ohms. Series means when you're running a race, you have to do them all. You have to go through all of them. That's what in series means, right? It's kind of like a circuit. All right. Well, that means if I want my amperage, or my current, we didn't explain why it's an I, did we? Intensity. I think that's right. It's because I don't like that one. So we're going to draw a name out. Who can tell me what my total current is? Carter Marsh. 5. I'm going to double check you because I'm not that good at math. 100, 20, 100, yeah, 5 amp. Thank you. Every once in a while I do one wrong, so make sure you speak up if you do, right? So 5 amps. Oh, very cool. Well, Kirchhoff would say we can't lose any of them. So let's put 5 across this guy. So we got 5 amps times 10 ohms. So how many volts are across him? 50. And we say volts, and it's going to be 2 points, right? So we want to know from this point to this point, if we put a voltmeter on there, what's that going to read? 50 volts. If I come down to this guy, I've got 5 ohms, 5 amps. So how many volts? 25. That's from this point to this point. And, well, it's the same thing. I can just redraw the triangle, right? 25, volt, 5, and 5. And here is where a good SMAT student will do that. They'll write it on their page, and they're going to ask you one question. What's the amperage total? 5. What is the amperage at resistor 3? 5. What's the amperage at resistor 1? 5. What's the voltage at resistor 2? 25. So that's how that's going to work. Have it on a piece of paper and then just fill them in. Now a good SMAT student will look at this and go, let's see here, let's make sure. 100 volts total. In series, they better add up. 50 plus 25 plus 25. All right, cool. Because if you messed up the math in this one and somehow you ended up with 20 here, 50 plus 25 plus 20, and we're at 95, and something went wrong somewhere, right? So, before you turn in your paper, it's a really good idea to just go through, make sure that it adds up correctly for all the rules we learned.
What is the unit that has to go around and do the same?
Amps. The amps. How many amps are going in there? And it's back to, if I line you guys all up with the airheads, if I put 2 in on one side, because we're not talking static, 2 are going to kick out the far ends. If I can phrase it that way. The amps will always be the same in a circuit. And it's because we need the exact same to come in as we go out, or out as we go in, or however you want to phrase it.
So the resistors aren't resisting amps, they're resisting the voltage.
Correct. Yep. All right. Kirchhoff, kind of a smart fella.
Those triangles around the outside there, those are calculating amps.
They're calculating anything you want to calculate.
No, I mean, is that the like single triangle 5 and 5 is 25 volts?
So 25 volts divided by 5, so the amps,
Oh, I see.
amps, amps, ohms, ohms, ohms. So whatever number I don't have, maybe I don't know how many amps I have. Maybe I know I have 25 volts and 5 ohms resistance. I do 25 divided by 5 and it'll tell me 5. But early in the question, we already decided that, because we knew the total, we knew there was 5. So if I got 5 here in series,
Just need to find
I know I have 5 here and here and here. And if I wanted to put an amp meter here, I know I got 5 there. If I want to put an amp meter here, I know I got 5 there. Because the amps through that, there's no extra path for it to go to. That's the next couple slides we'll go to. Okay,
Case.
yeah,
Just to make sure I'm understanding you correctly. 10 ohms plus 5 ohms plus 5 ohms equals 20 ohms, and volts works the exact same way. It's the sum
in series,
of
yep,
each load.
yep. That's how Kirchhoff does it.
Okay.
And remember, that's in series, that's why it's red and yellow, right? Isaiah,
When you're saying amps or amps,
yeah,
in like simplest form, what is that? Like,
it's 6.28 billions electrons per second,
over 1 point.
which is 1 column of electricity per second, passing that point. It's an amount of electrons going by. Yes?
So you said if voltage is measuring difference,
Pressure difference.
technically you're ending up with 0 going in the back? Because you said there has to be 100 amps going, if there's 100 amps coming out.
I got 100
Has to be going-
volts.
Sorry, 100 volts going out, there has to be 100 volts going in.
Well, volts isn't a thing. Volts is a pressure difference. So I have a 100 volt pressure difference between here and here.
Okay, yeah.
So it is 0 going in the back to back. Volts, pressure.
Pressure always has to be between 2 things, right? So I can't measure from one space to no space. So let's have some fun with this. I think it might answer your questions. If I put a voltmeter from here through my voltmeter and go back to here, what's my voltmeter going to read? I want to know the pressure difference between here and here. Well, that's the same thing as right here, right? The wires don't have any resistance. So I'm going to have 25. Because from here to here, the wires we consider at this point in life negligible. There's no resistance in the wire. So this, that's the exact same as this, right? All I did was like that. You guys see that? So if I want to put one, if I want to put a voltmeter to here, now what's it going to read? That one's a little trickier. 50, because I'm going to have this guy 25 plus this guy 25, so that would be 50. It's the difference between this side and this side, which happens to be 50 there. Check.
So one column is 6.28 billion, and an amp is 1 column per second.
Yep.
It sounds like it's a rate.
It's a rate. How many amps are going by every second? Yep. Yeah.
And you measure an amp from 1 point.
Yes. You put one gate in there and you say, how many amps are going by that gate, that point? Now, it will be the same anywhere in a series circuit because we don't stack up like static electricity. We all stay spaced out just right. So one way to explain that could be to put our boxes, remember when I did the boxes on the table? So if I put a box and I line this whole thing up with boxes, this could take a little log to draw. I'll do circles instead. All right, we're gonna say each one of those circles is, we'll make it fun, a column of electricity, 6.28 billion electrons, right? So if I were to measure my amps at that point, and I say I'm pushing hard enough that 3 of these boxes go by that point in 1 second, Well, the boxes aren't gonna compress or whatnot, basically. So if 3 boxes go by this point, if I wanted to measure it there, 3 boxes are gonna go by that point too, because we gotta think of it that way. They don't stack up, they don't compress. If I move them here, they have to move there. So you can kind of think of them like beads on a chain. Okay? Later on, when we start adding capacitors in, life gets weird, but we're not gonna go there yet. Capacitors are kind of like a storage depot for those little beads, and it just messes with life. But it's fun. It's a fun way to mess with life. All right, so that is in series. This is in parallel. Notice now, if you're a box on my little line, or an amp, if you want to phrase it that way, and we line those all up, you get the idea. Let's give ourselves our triangle over here, and we'll say 50 volts. And just for the fun of it, we'll give ourselves, I'm not going to do 50, that's going to make life too complicated. 60 volts, okay? That's going to help my math out. So 60 volts, we're going to say each one of these is 10 ohms. 10 ohms, 10 ohms, 10 ohms. All right, so if I have 60 volts from here to here, and the wires were saying there's really no resistance there, right? So that means I'm going to have 60 volts here too, right? Because connection-wise, there's nothing to resist me. So in parallel, I'm going to have the exact same voltage at each of these resistors, right? Because you can draw a line from that connection all the way back to the battery without going through a resistor or anything. So the pressure's not going to change, is basically how we're looking at that. So once we understand that, it gets pretty easy to do one that's in parallel. The idea is going to be we got this total of 60 volts, and I should have done the math, we'll do it here. If I have 60 volts and 10 amps, if I put a triangle up there, 60, 10, how much current am I going to have through there? 6, thank you. I did all the same numbers, so I could do it the same here too, right? 6 amps, 6 amps. So, if I were to push amperage, some of them are going to go down here, right? Some of them are going to take that path, and some of them are going to take that path, just like a road system where we're all going to split up and go our own merry way. But it still follows the rule. So if I've got 6 amps here, 6 amps here, 6 amps here, all of them came from here though, right? So how many amps left my battery? 18. 6 plus 6 plus 6. So 18 amps left my battery, amps. 6 of them went that path, 6 of them went that path, 6 of them went that path. And they all joined back up because we know it'd be 18 here, right? That's back to Kirchhoff. We can't lose any of our amps. They all got to do, if they come out, they go in. So that's how it works. So just for the fun of it, I can do this. So I got 60 volts, 18 amps. How much resistance total is there then?
3.3333.
Oh yeah, 3.3333 ohms. We can just do the math because we knew 2 of the 3, right? So there's a bunch of different ways to get to this. I'm going to show you a kind of complicated formula in a minute. The easiest way is, if you see the rest of the numbers on there, just do them. But you got to know the total resistance total. It's always going to be less than whatever the smallest one of those is, right? Because basically you've got a small amount of resistance, well you got other paths to go down, so it's just going to make it easier for traffic to flow. So the total resistance of a circuit will always be less than the smallest resistor that's in that parallel, right? So how we get that 333, the easiest way to do it, if the guy that did the math did you a favor, is to just look at it and go, oh, they're all the same. Well, that makes life easy, right? We can just do 10 divided by 3. That's going to give it to us, 3.3. That's like super easy math. Now, sometimes the guy isn't that nice to us. I'm going to come back to why in a minute. But just for the fun of it, if I wanted to pick this point here and put an amp meter in there and and say, how many amps are going down there? What would my answer be at that wire? Marcy, given everything else you know. How many amps right here? 12, yep. Because we're going to get these 6, that joined back up with those 6, right? So very good. 12 amps, and then once they catch up with the rest of their buddies, it'd be back to 18 over here, right? Everybody seeing that? All right, cool. So you can play all kinds of mathematic games. There's not a right and wrong way, per se, to say I have to do this one first or that one last. That's why I love electrical math. It's like a puzzle. How many of you, when you start a puzzle, start with the corners? Yeah, me too. Some people, they'll pick a picture in the middle and start from the picture. You can do it either way, as long as you follow all the rules. You'll both end up with the puzzle done at the end. Doing electrical math is the same way. So somebody that's good at electrical math, they'll look at the thing and go, is it going to be easier to start on the edges or start here? And they'll start picking out, oh, this will be super easy if I start there, and start plugging in numbers, and the next thing you know, the whole puzzle's done. Mr. White.
Okay, so you had 60 volts up top, and I'm trying to figure out the 3.33.
Okay.
What was that?
So total, if this is my total going in and out of my battery,
Yeah.
we had 60 volts,
Uh-huh.
and we're gonna have I, or current here, right? And we weren't sure what it was.
Okay.
No, wait, we knew what the current was.
18 amps.
18, I told you that. Did I tell you that one?
Yep.
Oh, you know what? I eventually got to 18 because I gave you one resistor. And that one resistor, I said, was 6 ohm. That's how we started. So once I knew that was 6 by 60 volts, 60 divided by, actually it was 10.
6 amps.
It was 10 ohms, excuse me. So it was 10. So I did the little triangle here.
Yep.
60 divided by 10 gave me 6 amps. So I did that one for this, and they're all 3 identical. So I know if I got 6 amps here,
Yeah.
I got 6 amps here, I got 6 amps here,
Okay.
and I know whatever leaves has to come back. So if I've got 6 plus 6 plus 6, I got 18.
Yep.
So that's how we came up with the 18.
Yeah.
Now that I have 2 of my 3, I can just do math.
And the ohms for this is the ohms for the entire circuit?
So, yeah, so you'll often have voltage total, amperage total, resistance total that it'll ask you. And then that'll also be for resistor 1, resistor 2, resistor 3. So we'll ask for each individual one.
Okay. I see.
Yep. All right. So here's the kind of crazy long formula, and then I think we'll take I'll check the PowerPoint, and we'll take a break. Here's a trickier one, right? So I didn't make it all the same. I got 2, 6, and 3. I didn't give you a voltage. If I don't have a voltage, it's one less piece of the puzzle to go off, right? So I'm like, oh man. I can tell you what the total resistance is, but I won't be able to necessarily tell you voltage or amperage on this one, because I would need one or the other of those factors. But you can just off the resistance itself do it. And the math is 1 over resistance total equals 1 over resistor 1, 1 over resistor 2, 1 over resistor 3. So if we write that math off, 1 over RT equals 1 over R1 is 2 ohms plus 1 over 6 ohms plus 1 over 3 ohms. So I hate fractions. So there's multiple ways to do this. One is you can just turn those fractions into decimals. The other is to turn them all into like fractions, and I tend to just turn them into decimals, okay? So what's the decimal of 1/2? 0.5. What's the decimal of 1/6?
1.16.
Pretty sure about that? I think you're right. 0.16 repeated?
Yeah.
Okay, and what's 1/3? That's 0.3. So, if you plug these into a calculator, 0.5 plus 0.1666666 plus 0.3, what does that spit out? makes it easy.
Assuming,
It messes up my math,
depending on how you're.
because then it's 1 divided by 1, which gives us 1, so I wouldn't have been a good one to put on the board. So we'll do it for one more, and we'll change it slightly. Let's change it to 5 ohms, 6 ohms, 10 ohms. We'll do the math again. Now, what you can do here, if you're a math genius, is you can be like, I don't like the 1 over top of it. So you can say, you know what? If I put this 1 on top of that whole thing, 1 over R1 plus 1 over R2 plus 1 over R3. This formula is the same as this formula if you like math. And what that'll do is it'll give you an answer at the end. So it's slightly simplified. So we'll plug that in and do it that way. So I'm going to move this formula up to here a minute. So RT equals 1 divided by, all right, so 1 over 5 is what? 0.2, right? A fifth. 1 over 6 is that 1.16, right? 1 over 10 is 0.1. So who can add those up for me? 0.1, 0.2. Did I mess the number up? Oh, 0.2, sorry. Is that better? That's better. All right, so now somebody add those up for me. 0.2 plus 0.46. So 0.46 repeated. All right, so then we can just take our calculator and do 1 divided by 0.46 repeated. 214 something or other. So resistance total is where's the decimal? 2.14 something, 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 something is resistance total. And we'd say, is that less than our smallest one?
Yes.
Yeah, so we probably did the math right. So that is how you can do it with the complicated formulas. I am like, I don't know if I like those complicated formulas, but sometimes you have to do that. It'll be one written test, is they'll want you to work through that. So figure out which way you want to do it, which math. The formulas are there, depending on how much you like math is there. I turn them into decimals and just try not to mess it up. You probably have to memorize this and or memorize this if you want to get 100 on your written. Check.
So I get 1 with the different fractions together, but then the answer is 1 over RT. Do we have to change anything with the final fraction?
You're going to do 1 divided by the final fraction you get. Because the 1 is 1 over on this side. So this is an easy formula to memorize. It's a little harder to work with because you get all done and you got your final, and then you got to take that answer. So let's say this plus this plus this equals, it's always going to be less than 1, generally speaking. Well, that's not a true statement. Let's say it ends up 0.67, well, that's weird. 673 is what those 3 fractions end up being. So that's 1 over RT. So you're going to say, okay, well, it's 1 over, so 1 divided by 0.673, that would give your final.
Okay, so you turn to a decimal and then you just divide.
Yeah, yep. I just do 1 divided by whatever decimal I get. People that are good with fractions, Christina, can probably leave those in fraction form, or they might, mess with denominators and stuff. I'm like, wow, that gets complicated. I'm going to show you a hack. Yeah, you can use your calculator for this. Here's a hack. Let's say we got I'm going to go a slide further. There's just your formulas again. Okay, let's say you've got a 5 and a 10 and a 10. And just for the fun of it, we'll throw in 100 volts. That's all the info we would need to fill in everything else, basically, right? Because we could start with our 100 volts and go to my triangle here, because each one of those is going to have 100 volts across because they're in parallel, right? So I could fill in my triangle 100 divided by 5, that's 20, I could have fun, we could start solving the whole problem, we could do it that way. So as soon as they give me voltage, I'm like, aha, I got you, I'm gonna cheat. But if they didn't give me that, I can still give you your resistance total. You could do that formula, which would be 1 over 5 plus 1 over 10 plus 1 over 10 is gonna equal 1 over my resistance total. And because I'm lazy, I'm gonna do that. And now I can plug in all my decimals and make it work, right? But here's the cheat. If I were to cut that section out, if I have two 10s, back to what we said, what would be the total resistance of that section? They're in parallel. Careful. 5. Remember how we had 10, 10, and 10? We said we just divide it. It can't be higher than the lowest resistance. It's got to be less. So if I got two resistors that are 10 ohms in a little, here, I'll redraw it. Here's your drawing. I go like that. Okay, so basically that's what I did is I cut that section out. 10 ohm, 10 ohm. So I just drew a little box around it and said, I'm going to pretend I'm only looking at that for a second, just for a second. And I say, what's the total resistance of this one? And you'd say, oh, well, it's going to be 5. The nice part is they're even, so I can just do, there's 10 with 2 of them, so 10 divided by 2 equals 5 ohms. Okay? So if the numbers of the resistors are the exact same, you can just divide the number of the resistors. So it makes it super easy. So what's fun is, let's say they give you this one, back to not looking at that little square. If I've got a 10 and a 10 and a 5, I could, in my little head of mine, I could be like, okay, I'm going to make an imaginary box here. Inside that box, I'm going to pretend instead of one resistor, I've got 2 resistors, and it comes out, okay? If I did that, if this total is 5 in the box, what would each one of those individual ones have to be in order to give me a 5 total? 10. So I'm imagining, right? So, if you're good at this kind of stuff, when you see a puzzle that's a 5, 10, 10, you can be like, oh, I'm on to you. I'm going to go pretend that inside this one, it's actually 2 separate resistors that are 10 each, which would give me a 10, 10, 10, 10. And I could then just divide 10 by 4. 1, 2, 3, 4. 10 divided by 4 is 2.25. 2.5. See, I'm bad with math. 10 divided, thank you. 2.5. So I just cheated. Did I use that big fancy formula? Oh, I just said, ooh, 5, I like 5s, because it's half. So I just told you that the resistance total of this thing is 2.5. Just by cheating, looking at that, going 5, ooh, I'm going to invent inside that little box. I'm going to make it 2 10s, make it 4 10s now. So we're going to do the math on that, and then we're going to take a break. We're going to make sure we come up with 2.5, and I'm not crazy. So if it's 5, 10, and 10, 1 over 5 plus 1 over 10 plus 1 over 10 equals 1 over RT. I gotta turn these into decimals. 0.1, 0.1, 0.2, 0.2 plus, whoa, how'd that happen? 0.1. 0.2 plus 0.1 plus 0.1 is 0.4. Alright, ooh, that's starting to look nice, isn't it? So, 0.4 equals 1 over RT, which means, how do I do that again? 1 divided by 0.4 RT equals, do it on your calculator, 2.5. So you can avoid those fancy long formulas by looking for clues like that. And the way I phrase it is kind of imagining, hey, let me take that section and I'm going to draw it internally just a little bit different. And I can do some math. So let's take a break. That's pretty much the end of the slideshow, but we're going to review that and do the math together a couple times. And then we're going to make it one step more complicated and do a complex circuit, which means there's going to be part series, part parallel, and it's really just adding one level to the math, not that complicated. So take a break, come back at, let's say 10 after. you're not getting it, come see me and ask a question.
Or when in doubt, throw it all into a bucket.
I
What?
like that.
Maybe you can help me.
Yeah,
So I tried to use this one here, so we have 5, 10, and 10.
okay,
So 1/5.1/10 plus 1/10.
okay.
That's right, equals RT.
You got two different numbers here for 1/10s.
Okay.
You did the same
Oh,
thing I
yeah,
did.
yeah, yeah. So
There
that
you
would
go.
be 1 divided by 0.4. Okay. Trying to figure out.
There you go.
Thank you.
Yeah, if you noticed when I was talking, I did the same thing until I heard some grumbling. I was like, oh,
Heard some grumbling.
Yeah.
Trying to wrap my brain around it.
oh, that's the wrong, you don't want that one. You want that one.
different, given a certain amount of ohms per year, and then we're trying to find.
Yeah, so let's say we do, just for the fun of it, 2, 4, and 4 ohms.
Yep.
In a beautiful world, we'd either give you the voltage total,
Mhm.
would be perfect, but I'm not going to. I'll give you the amperage total.
We can use prime digits, right?
Is 4 amps.
Well, it's parallel, so we're using the R1 plus R2 is R3.
Yep.
1 over that.
Yep, yeah, because each one of these, if my voltage
Yeah.
here, it's gonna be what it is here, right? Because,
So our voltage would be these added together.
not voltage, amperage.
Amperage.
Voltage is from 2 points, right?
Right.
Why would there ever be a voltage difference between any of those 3 points?
Okay.
They're all connected with a solid wire,
Right.
so that means each one would have to have the same voltage across them, is what that is.
So we need to find our amperage.
Yeah, which would be great, but we go, what, how are we gonna do that? About the only, well, and we have amperage total, but we don't know how many are going down each individual one,
Right.
right? So this is where most of the time you would go to the long formula and say, well, I have my total resistance, or resistances.
Right.
So can I find this with this info? They go, yep, we can use that fancy formula, right?
Yes.
So we would do 1/2 plus 1/4 plus 1/4.
Yep.
And it's 1 over all that is resistance total.
Makes resistance, so we got 0.5, 0.25.
0.25, 0.25.
Yep, add those together.
So those are gonna be,
135. Yeah.
so that'll end up with 1. So it's 1 divided by 1. That's fairly 1. Whoops. So my resistance total on that then would be 1. So now that we have 2 of these, we go,
Intensity is amperage. We need to find this.
yep. So now we have 2, it makes it easy. 1 times, I put that in the box, just for you. I mean, it doesn't really matter which side, right? 4 times 1 is,
Current times flow is amperage.
yep. 4 times 1, current is flow. Current times resistance.
Current times resistance.
Yeah, current and amperage are the exact same thing. So, current times resistance is voltage, so we put a 4 up there, which gives us a 4 volt total.
And we were looking for both of these numbers.
Well, really, we'd say, let's find every number we can find.
Right.
So now we would go back to these individual ones. We already know that the voltage is gonna be the same on all of them, right? So we can just put our 4 up on each one. We could put our resistance to 4,
Now we just work each one.
4, and you could work each one. 4 divided by 4 is 1. 4 divided by 4 is 1.
Right?
2,
So it's
2
true
plus
and
1 plus 1.
I think they're going for true.
So it doesn't matter which way we work it. So, the cheat on this, if you don't like this,
Yeah.
would be just to look at, oops, just erase my numbers there. You said 4, 4, and 2.
Yep, 4, 4, 2.
Alright, and I think that's what we started off. we started off with, right? So the cheat on this one would be, okay, if I'm looking at this, I could draw myself a little box and say, hey, let's make this one 2 resistors.
Yep.
And that's where we're imagining it.
I was trying to understand what you meant by like
Yep.
splitting it.
So we're imagining now,
Yeah.
but if that was 4 and 4, that'd give me a 2 total,
Right.
right? So if I removed that and put that in its place, now life gets pretty easy because I have 4 of the exact same 1, 2, 3 resistors. And I know the amperage is 4 amps if they're the same resistance. So I'm gonna have 1 amp, 1 amp, 1 amp, and 1 amp. Well, this was through 2, so the total amps through this one is gonna be 2 amps, 1 amp, 1 amp. So that's the way I basically solved it without having to do this.
Okay.
So by using your little imagination to say, I don't like those formulas, if the math adds up to where you can make the resistors in a parallel circuit all the same, you can avoid the complicated formula.
Okay.
So some of the exams, for instance, you either have to do that complicated formula,
Well, I
or
don't think it's terribly complicated, but I mean, it depends if you want to do it with fraction or decimal. Or
yeah.
that's more complicated.
So some of the writtens, for instance, will, let's give you a 2, 4, and 6. And I'll give you 3 answers, A, B, and C. One will be 3, one will be 9, one will be 1.5. You gonna do the math on that one? I'm not, because we taught you the rule. The total resistance has to be less than the smallest resistance, right?
Right.
So out of these answers, how many of those answers are less than 2?
Less than 2, none of them. Well, which one? These answers?
Yeah.
The 1.5.
It has to be that. Now, I didn't actually do the math, so I don't know if that one's right.
Right.
I'd have to go in there and be like, but I think I'm close. If I really wanted to have fun, I could go all the way to 12s. I could say this has 2 12s. This one has 3 12s. This one has 6 12s. I've got 6, 7, 8, 9, 10, 11, 12. I've got 12 total resistors now. Where was I at? There's some sort of math in there.
You're saying 12s because like if you were adding the fractions, you put
Yeah,
common
right.
denominator.
That's basically what you're doing. So come back to my common denominator at 12.
Yep.
So you could, so that's what, it's 12s that had 2 of them. That would bring me back to 6. But, so you could really avoid the math formula if you wanted. But I don't want to go that far. So where was I going with that one? I could get to, it's probably going to be not 1.5. You do the math, I'll do it that way. How was I thinking? I was going there for a reason. I was gonna draw that out. I was gonna say 1, 2, 3.
I guess I just need to work from
5, 6.
12 resistors. Or 6 resistors.
That should be
6 plus 3 plus 2.
It's times 3. Yeah, sorry.
No, yeah.
I was making it more complicated.
Nope, it's
I'd
alright.
actually have to have 6 2s. Yeah, I guess.
6 2s.
I'd have to have 6 2. Yeah, it's. I confuse you. Sorry.
It's okay.
You can.
I'll start working these problems.
Yeah, you'll do it, but you can figure out how high you gotta go, and the math will start working out. So let's double check. I just made the 1.5 up,
Yeah,
just by saying
it's gotta be less than,
it's gotta be less than. That was the point of what I was saying. But let's do the math once, just for the fun of it. 1 divided by 2, 1 divided by 4, 1 divided by 6 equals RT 107. It's 0.5, 0.25, 0.16. So just for the fun of it. 5 is those 2. 6 is gonna be 6 stays up here. 0.916. Am I in the neighborhood if I have that up? 0.916. Hey, I did it right. 6. Then I gotta do the 1 divided by that one. I don't know how to do that on my calculator. 1 divided by 6. 1.09.
that's the resistance on the coming off all three of them.
Yep, RT.
What I, RT? Alright.
The circuit total.
I wanna do that.
So I just quick threw one up that was below 2 to make that point.
Just check it, see if it's right or not.
So I should have, so the exam would have 1.0. So back to if you're doing that same thing, go back to, without doing all the math, if those were your 3 options, how do you know that's the right one? It's the only one that's less than 2.
That's, it's the most right answer.
Hey, my 12s. I got 1 divided by 12 is 1.09. It was in there somewhere. There was a thought somewhere. Whoops. All right. Let's wrap this up and get you guys doing your own homework. So, resistors in parallel, the amperages add up, right? Amperage 1, amperage 2, amperage 3 will give me my amperage total. Resistors in series, the voltages add up, but the amperage stays the same. See how they kind of flip-flop? So I'm trying to teach you the logic of it more than the math, but we taught you both. So you got to make sure that you have both of those straight in your head. Now, we go to a little bit trickier one and go, oh, this is a series parallel. Sometimes they'll call it a complex circuit. And they say, I don't know, is that series or is that parallel? And that's where we start chopping them up and using our imagination to solve the puzzle. So what we can do, that's the wrong color for what I want. What we can do is we can take that section and say, what's the resistance total of my red section? So maybe I shouldn't call it total. Resistance red. Resistance red will work. So we could do the math, 1 over 100 plus 1 over 50, you get that answer, and 1 divided by it. Or if you're like me, you go, ooh, those multiply by each other, right? So this one happens to be half as much as that one. So this I could even chop down smaller to say that's kind of like saying this, right? If I had 100 and 100. So 100 divided by 3 is 33. So RR is going to be 33 ohms. So whichever way you want to get to that is fine with me. Do you want to do the 1 over just because we're in learning mode for everybody? 1 over 100 plus 1 over 50 equals 1 over RT. Ooh, that's a 0.01 plus, well, what's 1 over 50? 0.02. Okay, so if I add those together, we're at 0.03. So 1 divided by 0.03 better be 33, I hope. Math's amazing, works, even when your brain doesn't. So you can get there either way. So, if my red resistance total is 33, and this one's 80, and double check, 33, is it less than the smallest one? Yep, okay, so 80, now we're back to all our ants are essentially, basically in series through our imaginary 1 resistor, right? So 80 plus 33 will give me my resistance total. So RT equals 80 plus 33, 113. Everybody see how we did that? Follow me? Okay. Now if I had a voltage, we could keep going. Why not? Let's do 24 volts for the fun of it. A lot of our aircraft are 24 volts. Now I can get my amperage. So I can just do my triangle. 24, resistance total is 113. Somebody do me a favor and do that math. 24 divided by 113. 0.21-ish amps. Alright, so that means if I put an amp meter in here, I'm gonna get 0.21. If I put an amp meter here, I get 0.21. Well, some of them are gonna go through here and some of them are gonna go through there, right? So we could figure that out, but let's just, I'll put this 0.21 amps. So let's just keep going. If I know I got 0.21 amps, they all have to go through this guy, right? So I could make him a triangle. I shouldn't have done it right there. I could make him a triangle. I'm not sure the voltage, but I know the ohms is 80. I know I got 0.21 amps. So 0.21 times 80. 16.8 volts. Alright, well with that, Kirchhoff would say we just made everything easy, right? Because if I got 16.8 here, these ones are back in parallel, which means they're going to be the exact same voltage. So we could go from here a bunch of different directions. Marsh.
So is that, the voltage that we just found after that, is that like the minimal amount of volts that need to like go through that EV?
It is the amount of volts that will be dropped across. It'll be your pressure loss across that resistor. At 80 ohms and that amps, the math says it has to be that.
So let's say, so if it's like a 10-volt system, then it won't work, right?
Well, the math would change.
Oh,
Yeah, it's just gonna be different math. Yep. Alright, so I can solve this a couple different ways. One would be, I can take my 24 volts and subtract 16.8. That would tell me how many volts are on each of those or both of those, right? That's one way to do it. I could otherwise go back to my red box and say, well, I know I got 0.21 amps, so I can go back to the red box and say amps equals 0.21. So I can make a triangle for the red box and say 0.21 amps, 33 ohms of resistance. I could multiply those two, 0.21 times 33. Somebody will do that for me?
6.93.
All right, 6.93. So we'll do it that way. So my red box has to be 6.93. They're in parallel, so this one's 6.93 volts. This one's 6.93 volts. Well, I got a resistance now, so I could just put those in. 100, 6.93. Oop, wrong box. 6.93. That will tell me how many amps are going through that one. Can somebody do that? 6.93 divided by 100. That should be easy. 0.0. Oh, sorry. 693. I made it too small. So if I have 0.0693 going through this one, out of 0.21, the rest of them have to go through here, right? So I could either just give myself another triangle, or I could say 0.21 minus that number is how many amps I have left here. So you can see, doesn't really matter which order we do them in, as long as we follow the rules. There's 100 different ways to solve that. It just depends. Do you want to start with the border of the puzzle? Do you want to start with the meat of the puzzle? The trick is being able to look at one and say, I can figure that out. I would look at that 0.0693 and say, well, 100 ohms, 50 ohms, I know I'm going to have twice the amperage, so I might just look at that 0.0693 and multiply it by 2, because it's half the resistance, and do it that way.
Where does that come from? 0.069?
We said we had 6.93 volts. And I don't remember why. It's just, it is what it is. One way to do it is 24 minus 16 is going to give us 6.93. And that's back to, we can do it 100 different ways. So which way do you want to do it? So I'll switch slides, we'll do another one. But the main point there is on these complex circuits, a lot of times you're going to grab a pen or a pencil and you're going to say, you know what, let's simplify that parallel down into a series and see what it would end up being. Oh, goodness gracious. That's pretty much as complicated as you'll ever see as far as somebody asking you to do the math. Until we get to capacitors and such. But the good part is, if it's that complicated with capacitors, none of the rules work anymore. So, the good news is, this is as bad as the math will pretty much ever get, right? So you go, okay, that's pretty complicated. But, we can draw a bunch of imaginary boxes. We can redraw this thing, right? So, these two, we could combine into just one resistor. So I'm gonna redraw this, making it basically the same thing, just laid out a little different. I do know everything has to go through that first one. Okay. From that first one, it looks like I can go just through, that's 6 ohms. I can go just through that one and make it back home, right?
So what are you doing there?
So I'm actually just redrawing it the way it is, but I'm making it a little bit easier to understand. Alright, so now I have 3 different choices that I can go down. I'll take this top choice and put it as the first one. 12 ohms, 18 ohms, 12 ohms, 18 ohms. Oh, and I'm back home. That's not so bad. Now we'll go down the next one. 3 ohms. Oh man, and it splits. I can either go through a 6 or a 12 and I'm back home. So now I'm going to split it. Go through a 6 ohm. Wait a minute, where'd I go? 3 ohms. I can either go through a 6 ohm and I'm back home, or I can go through this 12 ohm and I'm back home. Alright, and the last path is a little bit of a weird one. It would be from here, and it just goes and connects in front of that 12 ohm. That is a weird one. Who drew this? Alright, so I just redrew it in a slightly different format, right? It's the exact same wiring diagram. I just redo it. So you can play games like that. I don't think I actually had any intention of solving this one. I was just showing you, hey, we can change stuff. So one thing I could do once I simplified it like that is, this looks kind of weird up here. I could draw myself an imaginary box because all those points are the same around those, and say, well, 3 ohms, 6 ohms, solve that one. So this box, I'm going to have a volts, an amps, and a resistance. My total resistance, I know, is going to be, you could do the whole 1 over blah, 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 or we could say, well, that is 666. So 6 divided by 3, 2. And I could get into where I go, okay, well, if that one's 2, and you can solve the whole thing. So I'm not going to go through it now, because that is as hard as the whole thing would get that you'd ever have. But you could basically start working your way through, chipping through, and solving it. We'll come back to this later, and we will probably solve it, but we've got a month in this class, right? So a month from now, after you go back and we work through the super simple ones, I think I drew that a little funny there. After you go through the super simple ones, like just, hey, those are parallel. Oh, these are series. You'll practice your math until when something like that one pops up, you'll go, let me see how many numbers I got. I'll just start drawing triangles and solving it, and you'll surprise yourself. Some people will be like, I'm just going to get it wrong. But you can work through that. So just for the fun of it, I'm going to do it tonight. I'm going to take a picture of it. I'm going to be like, see if I can get the solution to that. Once it starts falling out, it's not as bad as you think. impedance, that's not this lesson, but a couple lessons down the road, I already talked about, sometimes if they use the word impedance, what they're meaning is total resistance to electrical flow, still labeled in ohms, but if we have capacitors or inductors in our circuit, it's just one word we're gonna use later. I think maybe your lab might use the word impedance instead of total resistance at one point. So if you read the word impedance, just be thinking, okay, impedance is resistance. Just a fancier version of it. Why did that just go up? That is it. I would work on lab 3, and if you get time, what does your thing say, lab 4? Or maybe you want to work on lab 4 and then go back to lab 3. But either way, basically your assignments so far are lab 1 and lab 3. And lab 4 is going to be tomorrow's tack on.
What about lab 2 and 3?
2, if you check your calendar, we have way, way later.
Oh, okay.
Because it's
That's what I was wondering.
identification. Yep.
I got no idea.
Yep. So basically, if you're checking your calendar today,